Find out in 5 minutes, how can a single beam of light cut through steel plates? From the brightly lit New York to the dazzling Tokyo and the prosperous and radiant Shanghai, light is always everywhere. Humanity has been constantly exploring, mastering, and utilizing light. A tiny LED lights up when powered on. But have you ever wondered how electricity is actually converted into light energy? And how do humans use a single beam of light to cut and melt through hard steel? Today, let us approach the pinnacle of human wisdom: laser. In daily life, how exactly is electrical energy converted into light energy for human use? When it comes to converting electrical energy into light energy, the first thing we think of is the LED, or light-emitting diode. When an electric current passes through, energy is transformed, but what exactly is the principle behind this? In the last century, people used tungsten filament light bulbs. An electric current passed through a high-resistance filament to generate intense heat, causing the atoms inside to move violently, thereby emitting both light and heat. However, this method was extremely inefficient. 95% of the electrical energy was wasted as heat, with only 5% actually converted into visible light. Since efficient materials for photoelectric conversion are scarce in nature, humans began to wonder, can we artificially synthesize a new type of engineering material to achieve more efficient light emission? Thus, scientists combined nitrogen and gallium to synthesize gallium nitride GaN in a high-temperature vacuum environment. Using the Mach process, they allowed it to grow uniformly on a heated sapphire substrate. In this way, humanity discovered a key material with extremely high photoelectric conversion efficiency at that time. But how exactly does electric current turn into light in gallium nitride? We have to start with atomic structure. Atoms are surrounded by electrons. If we compare an atom to the Earth, electrons are like the moon orbiting around it. When an electric current is applied, electrons gain energy and break away from their original stable orbits. This is what physics calls an electron transition. However, the high-energy state is unstable, and electrons eventually return to their original low-energy orbits. During this transition back, they release the excess energy in the form of light. This released energy is not largely converted into heat in gallium nitride. Instead, it is radiated directly in the form of photons, the light we see. It is through the combined effect of electric current and gallium nitride that electrical energy is efficiently and precisely converted into light energy. Humanity has successfully harnessed ordinary visible light, but how exactly has this gentle light transformed into laser beams that can easily cut through steel plates? We have learned the principle behind LED light emission. Essentially, electrons release energy as they fall from high energy levels back to lower orbital levels. This process is called spontaneous emission. However, the photons emitted in this way are scattered in random directions and have inconsistent phases. They are just ordinary natural light. Albert Einstein once proposed, if an atom in an excited state encounters an incoming photon whose energy exactly matches the atom's energy level difference, it will, stimulated by this photon, emit an identical photon. What does that mean exactly? Imagine some atoms are already at the energy level 2. When an external photon comes in, and its energy exactly matches the energy difference between level 2 and level 1, it stimulates the atom to immediately drop from level 2 back down to level 1. During this transition, the atom emits a new photon, and this new photon is identical to the incoming one in every way. So one photon becomes 2. These 2 photons then go on to excite more atoms at level 2, causing them to transition and emit 2 more identical photons. This process multiplies rapidly. 1 becomes 2, 2 become 4, and so on, like a chain reaction. This continuous multiplication of photons is called light amplification. And this whole phenomenon is known as stimulated emission, the fundamental principle behind how laser light is created. But there's a critical problem we still need to solve. In reality, most atoms naturally stay at a low energy level. As a result, when an incoming photon passes by, it will mostly be absorbed by atoms in the ground state, exactly the process we saw earlier in LED lighting, known as spontaneous emission. What we need instead is more atoms at high energy levels and fewer at low ones. Only then can light passing through trigger amplification rather than being absorbed. This reversal of the normal energy distribution is what we call population inversion. To achieve this, a pump source is designed. It integrates a laser chip and an optical coupling system internally. The semiconductor chip efficiently converts electrical energy into light energy, and the coupling system then precisely focuses the light and injects it into the ytterbium-doped fiber. Why use ytterbium-doped fiber rather than ordinary fiber? Ytterbium is the particle we mentioned that achieves population inversion. Within the fiber, ytterbium atoms are continuously excited by light emitted from the pump source. A large number of ytterbium atoms are elevated to high-energy states, successfully achieving population inversion inside the fiber. At this point, only one key trigger is needed to achieve light amplification and initial photon with perfectly matched energy. As it happens, a small number of atoms cannot stably stay at the high energy level and will spontaneously drop back to the lower energy level, releasing a photon in the process. The moment this initial photon appears, it instantly stimulates surrounding atoms at the high energy level, setting off a chain reaction of stimulated emission. Photons are continuously copied and multiplied, and the optical energy is sharply amplified. This is how laser amplification is fully realized. However, at this point, the direction of photon propagation is still chaotic and disorderly. This is where the resonant cavity comes into play. It consists of mirrors at both ends, which confine photons to bounce back and forth inside the cavity. Photons keep multiplying as they travel back and forth, while those with random directions that cannot form an effective beam are gradually filtered out and eliminated. In the end, only high-energy beams with uniform direction and consistent phase are emitted through a small aperture in one of the end mirrors, pass into the transmission fiber, and then reach the laser cutting head. The focusing lens inside the cutting head converges this high-energy beam into an extremely fine focal point, as thin as a strand of hair. The extremely high energy density instantly causes localized intense heating, melting, and even vaporization of the steel, enabling precise cutting of the metal. So now we've covered the full story, how electricity is converted into light, and how ordinary light is amplified and focused into a laser powerful enough to cut through steel. Feel free to leave your thoughts and follow us for more. Zorier, your professional supplier.